This is Byron Devries, and this talk is on analysis and monitoring of cyber-physical systems via environmental domain knowledge and modeling. So, when we think about uncertainty in the environment or modeling the environment, is it sufficient to just identify the obstacles or enumerate the obstacles or problems? And it's really not, because there's just too many things, and it makes it infeasible to enumerate them all. Worse, even if we did enumerate them all, it might change over time. Now, other people have worked on things like searching for specific problems that could arise, but that has its own difficulties, because if we come up with scenarios that could cause an issue for our system, we now have to determine whether or not they're actually feasible in the real world. And once we start making that determination of if they're feasible, we've gone back down the road to what if the environment changes over time, and it is likely to. So our proposed solution is to model the environment as a communicating system. So we have a system that communicates with another system that just happens to be the environment. In this case, we're going to monitor or model a baby monitor that creates an alarm sound whenever there's either no weight or insufficient weight and no motion coming from the environment. So we have a child in a crib, and we have a set of sensors that determine whether or not there's any weight or any motion, including breathing, in the crib. And this is very similar to an actual baby monitor that I had with my first child. Now, the goal of this baby monitoring system is to keep the child safe, right? And the way it does that is it either attempts to achieve a safe child, or the child is already safe. Right? And if the child's already safe, then we have the correct weight, we have motion, and so we're not going to set off the alarm. But if there's an unsafe child, that means we don't have the correct weight, we don't have motion, and so we're going to set off the alarm, right? Because if we don't have weight or we don't have motion, either one of those things alone is sufficient that we want an alarm, right? Now, similar to that, we now have to model the baby monitor environment. And you'll notice here that we have sensors for weight, sensors for motion, and an alarm actuator. Well, when we model this corresponding environmental system, we're going to have the opposite of that. So we're going to have something that creates weight, creates motion, and senses an alarm. So we have a maintain environment goal model, and the environmental scenarios that we've modeled are either the child is not in the crib, and if the child's not in the crib, then we have to achieve a low weight and no motion, in which case we expect an alarm. If the child is in the crib, then it's possible that the child is not moving, in which case we'd still expect the alarm, and we'd expect a weight, and we'd also expect no motion. So those are two problematic environmental scenarios. Or the child is moving, in which case we would expect motion, we'd still expect that normal weight, and we would not expect an alarm. And you'll see that the weight actuators and motion actuators are there along with alarm sensors. Right? And so these two different systems correlate based on the actuators and sensors representing these goal modeling agents. Now, if we think of the satisfaction of this entire system, we can think of really what we want is we want to be able to have a satisfied environmental model, meaning that we've enumerated the right things, and in all of those situations, the system is satisfied. And so we can verify at design time that given our environmental assumptions, we've created a system that works appropriately. And we could verify this in a variety of ways. But what happens if the environment changes? What if it was incomplete to begin with, or even just incorrect? Well, there's a handful of scenarios that could occur. First, we could have a real world scenario that occurs, and it's also in our environmental specification. Well, that's good, right? Because we've verified that our system works appropriately in that scenario. We could have a real world environmental scenario that just never occurs, but we did model of it in our environmental scenario. And so we took the time to verify it at design time, but it just never occurs, in which case there's really not a problem there either. The real problem comes along when a real world environmental scenario occurs, but we didn't include it in the environmental specification. And these types of things could be broken out into kind of a Venn diagram where we have our enumerated environment here. And we have things that are incorrect notes, things that we just included but shouldn't have been included, right? And those don't really hurt us because they never occur in the real world. We have our correct set, our known knowns, are things that we actually have enumerated in our model and actually occur. The problem, though, is that we've got these things that occur that we didn't model. Well, what do? Well, again, we can't just enumerate every single feasible real-world scenario, and even if we could, they would change over time. So we've got to do some runtime analysis. And so what we're going to look for is we're going to look for situations outside of the one that we want where either one of these things is unsatisfied, right? So if the environmental model is satisfied and the system's satisfied, we should have caught that at design time, and we know the system has failed. But there's two situations where the environmental model is unsatisfied, and so we can't tell if the system has truly failed or not. And it's very dangerous to assume that the system has succeeded if we haven't verified that it succeeds in that situation. And let me give you an example of this. Here we have our baby monitor, and what we've done is we've actually given it concrete values and assessed whether or not each of these goals, requirements, or expectations would be satisfied. And we have a weight of 18 pounds. There is motion, and so we're not turning on the alarm. Well, the problem is this weight of 18 pounds is actually the weight of both the child and a cat. And for any parent that has had a cat and a baby at the same time, you probably know that one of the concerns is that the cat will actually join the child in the crib, snuggle up to it because it's warm, and smother it, right? Which could unfortunately kill the child. We don't see that in our system. But if we look at our environment, we see that we've got motion, we don't have an alarm, but we've got a weight that's outside of the range that's expected. And so the environment that we have set up is unsatisfied. And so even though our system appears to be satisfied, we know it's not in a situation that we actually verified it at design time. Therefore, this is an unenumerated or unexpected environmental scenario. We should perform some other operation to prevent this, a failsafe perhaps. And this failsafe would likely be just to cause the alarm to go off, right? Now, there are some limitations to this. All of this assumes that the specifications of the system and environment are correct, or at least correct enough. That there is some ability for the environment to be incorrect. That's kind of the point. If the system can't distinguish between environmental scenarios, though, due to limited sensors, that could lead to incorrectly assessed environmental scenarios, which would be problematic. And so, in summary, what we've done is we've presented a design and runtime approach to verify systems and detect unexpected scenarios at runtime outside of what we know. We've demonstrated it on a baby monitor system, and hopefully we'll have some future work that includes extensions for things like temporal and relaxed operators, adaptation in these unenumerated environmental scenarios, and the distribution of sensors for multi-system analysis. All right, thank you.